When we looked at gravitational potential energy, we realized that both the mass and the height affect the amount of energy it has. The one thing I couldn't show you was gravity. You see, gravity changes depending on your planet that you're on, but that definitely affects the amount of potential energy you have and how much you'll fall. We know that the gravity on the moon is less. Therefore, you might have a drop of 10 meters off the spaceship onto the moon, but you're not going to hit with as much energy because you don't have as much gravity pulling you down. The formula for calculating gravitational potential energy is this. Gravitational potential energy is your mass times your height times the gravity. Now, mass in this case is always in kilograms. Height is always in meters. And gravity, which is a constant here on Earth, is 9.8 meters per second squared. Now, likewise, motion kinetic energy has its own way of being calculated. Okay? We actually calculate it like this. It's going to be a half of whatever our mass is times our velocity squared. So again, we need to know the mass of the object that's traveling, and again it has to be in kilos, and we have to know the velocity, which is our speed in a direction. That's all that means. So we often refer to that as speed, and you need to know that in meters per second is how we measure our velocity, and it has to be squared, which means it has to be times itself. Now, these might seem difficult calculations, but it doesn't actually take much to work them out. We only need a speed meter to measure the velocity of something when it's falling or moving, and it's quite easy to measure the mass. And again, it's quite easy to measure the mass and the height for gravitational potential energy, and you know the gravity. So once you know essentially your mass, your height, and if it's moving, its speed, you can work out an object's gravitational potential energy and its kinetic energy while it's moving. Let's work out gravitational potential energy and kinetic energy in a simulation. Say you're in a yard which wrecks cars, and you need to design a machine that's going to put enough kinetic energy into a car to crumple it quite quickly. We need to know whether or not we've got enough energy being put from the wrecking ball into the car to squish it. So we design this wrecking ball with this mass of 1,000 kilograms, and we're going to drop him from a height of 10 meters. We calculate his gravitational potential energy as this: his mass times his height times gravity, which equals 1,000 kilograms times 10 meters in height times 9.8 meters per second squared for gravity. That equals 98,000 kilojoules of energy that wrecking ball is going to have before it drops. Now we need to see how much kinetic energy is actually being released or outputted by this as it hits the car. To calculate the kinetic energy, we know that we need to know the mass and its velocity, or its speed, just before it hits the car. Mass is easy. That was 1,000 kilos. Velocity, we just need to take out a little speedometer, and let's say they measured it and found that it was going at 12 meters per second when it hit the car. Let's put that into our equation. That is a half times 1,000 kilograms times 12 meters per second squared. 12 12s, you know your multiplication tables, are 144. So let's do this. We've got 144 times 1,000. Half of 144 times 1,000 is half of 144,000. Half of that, 72,000 kilojoules. So if they said we needed a minimum of, say, 60,000 kilojoules to squish the car, that means we've got enough energy there to definitely squish it. But we are losing some. If we draw our energy chain now, we started with gravitational potential energy and turned it into kinetic energy of motion. Our gravitational potential energy input was 98,000 kilojoules, and our kinetic energy output was 72,000 kilojoules, meaning that we lost 26,000 kilojoules through heat and sound.